I'm Saugato, and I would like to talk about my research on image enhancement for unconstrained environments. We are discussing digital cameras, their image acquisition process, noise characteristics, their source, and how we improve image illumination and handle color degradation. We are also discussing ways to create good quality synthetic data, which is required by most of the super resolution GAN networks for their training, and also how these kind of models behave on different data sets. Images are formed due to photoelectric effect. Incident rays hit the image sensor with unique energy levels and form patterns of charged pixels on the sensor. After we get the pattern, we apply mathematical operations to get the final image. As ideal or non-ideal based on several factors, and most of them are based on how easily we can process or infer from these images. In later sections, we will discuss some of these factors hindering the image quality, which are noise, improper illumination, and decolorization. Improving non-ideal images, we need to understand the camera's image acquisition process and the Retinex model. Another important factor that affects the image quality. Based on the source, there are three types. Short noise is the randomness of incident photons. The more the number of photons, the more will be the short noise. It is proportionate to the square root of signal. Read noise is due to the inaccuracy of the sensor's readout circuitry. This noise is specific to each camera and is usually dealt with by the manufacturer. We assume this noise to be constant for our experiments. The third one is the dark current or the thermal noise. This is due to the random photons released from the sensor itself due to its heat. For our use case, low light images affect the performance of computer vision and image processing tasks. In the first example, we can see that the number of OR features detected in the low light image is much lower than in the normal image. The face detection algorithm also fails to find any faces in the low light image while it succeeds in the normal image, as shown by the bounding boxes. A camera system goes through several steps to acquire an image. It begins with the photoelectric effect capturing the photons pattern and ends with the image formatted in sRGB. The enhancement methods treat denoising and illumination as separate problems and assume that the noise is Gaussian, which is not very realistic. They also use data-specific enhancement that are not generalizable to different datasets. For example, some methods convert the image from RGB to YCBCR color space and modify the Y channel histogram, but this may not work for all images. Use neural networks to model noise and enhance images. They train on paired data, where one image is noisy and the other one is captured in good conditions. They also compute an illumination invariant color map for image enhancement. The problem with these paired data is that they are hard to obtain as they need images to be taken in different lighting situations, which requires human effort. Needs good data that is both high quality and abundant. One way to get high quality data is to capture real paired images, one in low light conditions and one in bright daylight. However, this method is labor intensive and impractical as it is hard to capture images with same context in different lighting situations. Other methods of creating datasets have used techniques such as reducing the brightness of well-lit images to capture underexposed ones, or taking pictures with short exposure times. However, these methods do not model the noise properties well, which are very important for training these models. A neural network that is based on a modified version of the Retinex theory, which accounts for noise. To train our network, we develop a framework that can generate synthetic low-light paired data, which are essential for making the network learn realistic low-light image characteristics. We also evaluate our method on different datasets and applications to test its robustness. The network compares the low-light image and the reference image using a color map. measuring the reflectance component. This helps to avoid the issue of different reference images having varying illumination or reflectance levels. It also uses histogram equalization to enhance the contrast of the illumination component in the image. For the noise component, the network generates a gradient map from the color map data. It transforms the sRGB images from the dataset into their raw versions, then adds noise and reverses the process to get the sRGB images with noise. To do this, we followed the image acquisition steps of the camera systems and use the parameters from the Tramset dataset for some of the steps that are like black boxes. Our second module is based on the LLFlow neural network. We train it with the paired data generated from our previous module. The trained model is used for inference. We experimented with different variants of our data by changing some of the steps in our first module, and then we compared the performance of our variants with the pre-trained model. That having 500 image pairs, where one is dark and the other one is normally exposed, and they were captured with the same camera and settings but with different exposure times. We modified this dataset to generate synthetic data for training the network. We use the paper robot's built-in camera to capture 12 pair of real images, where the dark one was captured with the lab lights off and the bright one was taken in lab light on. We only use this dataset to evaluate the model, not to train it. This dataset contains about 11,000 images having human faces in low light conditions. We use this dataset to test how well our architecture can improve face detection. Earthcam images of the New York City skyline from June 6th to June 8th of this year, where the Canadian wildfire affected the East Coast and the rest of the world. These images helped us to better understand the performance of GAN networks. On the LOL dataset, which has 485 images for training and 15 for testing, we also experimented with different variants of the dataset that we created by changing some of the steps in our first module of the architecture, which is a process and process module. We trained the network on different versions of our synthetic data. We use some abbreviations to name our models, which can be explained. Raw means that we added short plus read noise to the raw versions of the dataset images and then converted them back to sRGB format. No CCMWB gain means that we added noise without using the column correction matrix, white balance, and digital gain steps. Pre-trained means that it is the model that the authors originally trained on the unmodified LOL dataset. V2 and V3 indicate whether the validation dataset was modified or not. V3 indicates that we trained on the modified dataset but validated on the 15 unmodified LOL images for evaluation. Whereas V3 means that we modified both the training and the validation datasets in the same way. We used V3 to make sure that our network does not overfit to our modifications. We compared the models based on three matrices: PSNR, peak signal to noise ratio; SSIM, structural similarity index measure; LPIPS, learned perceptual image path similarity. The first two depends on pixel values, but LPIPS is based on features that are preserved in the enhanced images. It computes the distance between the activations of two image patches using some pre-trained CNN models like BGG or AlexNet. Our best model is the custom V3 raw noisy, which we evaluated using mean, standard deviation, and variance. This model performed well on all versions of our data, so we can assume that it is the most consistent among the others. Performance of the custom V3 model on two types of noise: additive wide Gaussian noise and the short plus read noise. The model that was trained on the short plus read noise did better on most of the matrices. than the model that was trained on additive white Gaussian noise. Results show that the custom V3 model performs better than the others on paper dataset. However, we cannot compare the performance for the EarthCam dataset because we don't have a proper reference image to calculate the matrices. Outputs. Output of the model, which is similar to the reference image when it takes image C as the input. Image C is the result of adding noise to the original low light image from the pair. Image B and C are the original pair dataset. Results between the custom V3 raw noisy versus a pre-trained. It's visible that the custom model maintains better exposure and preserves details on the image whiteboard. Compares how good face detection models are at finding faces in images that have been enhanced versus images that are still dark. Works much better with the enhanced images than the original low light ones, but for face recognition, we need the fine details that are lost after image enhancements. It produces different results for each image pair in the outcome dataset. The left image is a reference and the right image is a model output. The model does a good job of enhancing the image quality for pair AB. For the pair CD, the model brightens the image but also loses some details in the buildings. The model fails to process pair EF, which is cloudy and lacks details. The model also fails to handle the context for the last pair, which creates unrealistic artifacts. Adding short and read noise to the images during training improved the model's ability to enhance the images. However, there is still room of improvement as a model does not have enough contextual awareness and sometimes produces unrealistic images. Our aim is to make the model aware of the context and the type of noise in the input image so that it can tailor the enhancement for each image. Everyone.